A ball is thrown off the roof of a building at a 51-degree angle with an initial velocity of 13 meters per second, and it lands on the ground below 59 meters away from the wall. How tall is this building? So this is a two-dimensional motion problem where the location of the launch is a higher elevation than the location of where the ball actually lands. So this one's going to be a little bit more complicated than the example I had done in my previous video. First of all, let's draw the situation. A ball starts off on the top of a building. It's given an initial throw, which will be VI, and that's going to be 13 meters per second. The ball will travel in a parabolic path until it reaches ground. Let's go ahead and calculate the VIX and the VIY for this launch. So just down here, VIX equals VI cos theta, and we'll have VIY equals VI sine theta. Our launch speed is 13 meters per second, angle of 51 degrees. .18 meters per second in the x direction. .1 meters per second in the y direction. All right. Now, when the ball leaves the building and comes back to the same position that it had been launched from, at that time, interestingly, the speed of the ball will equal the speed of the launch. But when it falls farther toward ground, the final speed here will actually exceed the 13 meters per second. It'll be much more. And I don't know what that V final will be. So it's unknown. And that's going to mean that the vertical component of VFY is also going to be unknown. However, we do know that VFX will match with VIX. It'll still be 8.18 meters per second horizontally. That's because Earth only pulls down, not to the right and left, so it can't accelerate an object in the x direction. One additional piece of information that we're given is that the ball will land 59 meters away from the base of the wall. So let's write that in. Delta x equals 59 meters. All right, now sometimes we have to start a motion problem with the horizontal dimension, and sometimes we start it by analyzing the vertical dimension. Depending on what we're given, it could go either way. And sometimes you could start by analyzing the horizontal dimension and then realize that maybe you won't be able to solve it that way. Maybe you'll have to analyze the vertical instead. If we choose to analyze the horizontal dimension first, then we'd be using the formula delta x equals Vx times t. If, on the other hand, we want to look at the vertical dimension, Then we might use formulas such as delta y equals 1/2 ayt squared plus viyt. Or we might use viy squared plus 2ay delta y equals vfy squared. Or even delta v equals ayt. In order to decide which one we should start with, let's write down on the side what quantities we have. Now, we have Vix and Viy. We also have Ay. Anytime we're dealing with free fall, the acceleration due to gravity will be negative 9.81 meters per second squared. What else? Delta x was given. Okay, so that's quite a bit. What about things that we don't have? Let's write those down as well. I notice that we don't have delta y, for example. That is what was asked for. Delta y is going to be the change in vertical position for the ball from the initial launch to the final impact. That would be delta y. We don't have the time of flight. We don't have the final velocity in the vertical dimension. That would be this here. Not sure how long that is. So there we go, 3 unknowns. Now it may be possible that you can use what you have and go direct to what you want. Notice that this is what we really are asked for. So let's look through the formulas and see if there's a direct path from what we have to what we want. I see that this formula involves delta y, and so does this one. The problem with the top one, though, is we wouldn't have the delta y, and we wouldn't have the time either. So that would be 2 unknowns in that formula. It looks like we can't solve it with that alone. Let's check out the next one. We don't have delta y. We do have viy. We do have ay, but oh, we don't have vfy. So we can't solve it with that one alone either. Now, by process of elimination, eventually we're going to find a formula that could take us to the next step. And that next step might not be delta y. All right, so according to this analysis, we cannot go directly to delta y through the vertical dimension. We can't do any of these formulas right now. So we've realized that we actually picked the wrong dimension to start the problem with. We want to start where we have more information. We want to start with the horizontal dimension. So sometimes it takes just running into that roadblock to realize that, okay, we can't start the problem that way. We've got to approach it a different way. And the reason why the horizontal dimension is the one to look at first here is because we know the delta x. All right, let's plug in what we have. We have the delta x. We have the velocity in the horizontal dimension. It's this. So we can solve for the unknown time. That's what it takes, is just looking through the formulas and seeing which one is viable. Which one can we get some progress from? T equals 7.21 seconds. All right, so that's going to be our time of flight. Let's fill it in. Now that we have that piece of information, it will be possible to solve this problem using one of the other vertical dimension formulas. And the one that jumps out at me here will actually be this one. Now that we have the time, we have everything for the right side of the formula, and we'll be able to solve for the delta y. Let's plug it in. All right, it's critical to plug in the right quantity for VIY. Sometimes people will plug in the speed of the projectile, the 13 here, but that would be wrong. We have to go with this vertical component of it because that's what matters to the y dimension. Y dimension doesn't care about the x dimension. All right. Delta y comes out to be negative 182 meters. It's negative to indicate a drop. So we started off at a higher elevation than we ended up at. So that's why the delta y is negative. And so that'll tell us that our height of the building is 182 meters.